So once upon a time, back at the first couple days of class, we talked about the additive law of exponents, and I don't remember whether we talked about fraction exponents, but I think we did, and I'm going to do a super quick review. So just as a reminder, in terms of that additive law of exponents, it's coming from things like if I had 5 squared times 5 to the 4th, notation wise, putting that little 2 up there as an exponent means that this is 5 times 5. And that 5 to the 4th means that I had 5 times 5 times 5 times 5. And I know I've done this a lot of times and I'm gonna keep doing it. So that's a total of 6 of those 5s altogether, which means I can shorthand write that as 5 raised to the 6th. And then we talked about the shortcut to get there is to see this as 5 raised to the 2 plus 4. And that's really fundamentally what our additive law of exponents is. Then we went on to talk about exponents being 0 and negative. And now we're finally coming back around to talk about exponents with fractions. So let's say that I had 4 to the 1/2 power times 4 to the 1/2 power. Well, our additive law of exponents would say this is 4 to the 1/2 plus 1/2, and 1/2 plus 1/2 is 1. So really, this is 4. So if I'm not sure what this 4 to the 1/2 power means, it's saying I've got some number, and when I multiply it by itself, I get 4 back. What's the only number I can put in there? It wasn't a trick question. Well, I think if I put 1 times 1, I'm not going to get 4. I think if I put 1 times 4, I definitely get a 4 back. Unfortunately, this says I have 4 to the 1/2 times 4 to the 1/2, meaning whatever goes in those 2 boxes has to be the same number. So the only number I can possibly put in there is 2. So 4 to the 1/2 is equal to 2. Now, there's another notation for that 4 to the 1/2 that we see pretty often. And that other notation is to write that as a square root of 4. But these are just 2 different notations for the same thing. I will let you know that although the square root shows up all over the place, when it comes to doing actual calculus with it, we almost always want to rewrite that as a fraction exponent. I think square roots are maybe easier or more comfortable for our brains, but that fraction exponent is the thing that ends up being more useful for us as a tool. Similarly, I can write the same kind of statement to say if I had 9 to the 1/2 power times 9 to the 1/2 power, additive law of exponents gives me that's 9 to the 1/2 plus 1/2, or 9 to the 1st power. And now I'm thinking about, okay, I got to put something in the box, but these are the same. So what goes in both of these boxes to multiply and give me 9? Yeah. So 9 to the 1/2 power is equal to 3, or I can write that as the square root of 9 is equal to 3. There are some things that are important for us to know about square roots. And really this next piece is a notation thing. Or I'm calling it a notation, you could call it a rule. But if I take the square root of 9, this is equal to +3, period, always. Now, some of you might be thinking in the back of your head, wait, I thought we were supposed to do plus or minus 3. And if that is something that is tumbling around in your brain, I want to address why that's happening. So this square root property, it's like undoing something being squared, right? So the square root of 9 is equal to 3 because 3 squared is equal to 9. They're going to like undo each other. The square root of 4 is equal to 2 because 2 squared is equal to 4. There's just this minor problem. -2 squared is also equal to 4. Some old dead white guy mathematicians decided that when we take the square root of a number, we always get the positive answer. They made the choice and we're stuck with it. So where that plus or minus thing comes into play is if I started with something that looked like x squared is equal to 4, and I was asked to solve for x, this equation has, and I was asked to solve for x, this equation has 2 solutions. If I'm solving this equation, I'm going to get that x could be 2 or -2. But personally, I'm not going to get there from taking the square root, although we could. Personally, I'm going to solve this by subtracting 4 from both sides and getting that factored. That's how I'm going to get that x is 2 or -2. But you could also take that x squared being equal to 4 and think about taking the square root of both sides. And when you do this in the act of solving it, that's when you have to remember that x could be plus or minus 2. Now there's an even mathier thing that's happening here, but we'll probably save that for another day. I will just say that we define the square root of x squared to be equal to the absolute value of x, and that's why we're getting 2 answers. Now, mostly none of that is going to matter for this homework assignment. I just like to address it up front because the square root of 9 is 3. It's not plus or minus 3. The square root of 16 is 4. It is not plus or minus 4. The square root of a number is defined to be positive. Cool. Now let's talk about some really annoying instructions to problems like the word simplify. It is my least favorite algebra instruction. So let's say that this thing that I've been asked to simplify looks like, how about the square root of 20 divided by the square root of 5. Well, there are some properties of exponents that we're going to have to work with here. We can work with them in the context of square roots. We can work with them in the context of fraction exponents, and it's completely up to you. But one of the things that I can do is to rewrite that and put all of it inside of one square root. And if I've put all of that inside of one square root, 20 divided by 5, last time I checked, was 4, which means this is the square root of 4, which means the answer would be 2. I don't know if you've noticed, but with lots of the stuff we're doing, whether we're talking about fractions with numbers or rational expressions or distributing exponents or the order of operations, multiplication and division kind of get grouped together and have ways that they behave, and addition and subtraction get grouped together and have different ways that they behave. So if I had an expression that looked really similar to this, but instead of being division, it said the square root of 20 plus the square root of 5. I cannot put these things underneath the same square root. Now, to help like solidify that, I like to just think about one example of something that I can definitely do in my head. So if I had the square root of 9 plus the square root of 4, both of these I can do in my head. What's the square root of 9? What's the square root of 4? And if I add those together, I get 5. That is not the same as sticking the 9 and 4 under the same square root. I don't know what the square root of 13 is, but if I pulled out a calculator, it would not be equal to 5. Which means that if I had to simplify this, I'm going to try other tactics. So one tactic that I'm going to try is, yes, factoring. We love factoring. We factor with variables and we factor with numbers. If I had to factor that 20, I would factor that 20 as 2 times 2 times 5. There are lots of different ways to conceptualize this, but I'm going to write that as the square root of 4 times 5. And then because I have two things multiplied together under that radical, I can break that apart as the square root of 4 times the square root of 5. So when I have multiplication or division, I can stick those together under the same radical. But when I have addition or subtraction, I can't do much with them at all. Now I can say that the square root of 4 is equal to 2. And here's where we kind of get back to that idea of like terms. So I've been using this radical notation, but if I were to switch and to use this as fraction notation, this would look like 2 times 5 to the 1/2 power plus 5 to the 1/2 power. I have two terms with the same base and the same exponent. That means these are like terms. I've got 2 of these 5 to the 1/2 plus another 1 of these 5 to the 1/2. So when I combine those like terms, I end up with 3 of those 5 to the 1/2. Now, if you don't like the fraction exponents, that's totally fine. We could have done that on the previous step as well. When I've got a square root of 5, 2 of these square roots of 5 plus 1 more of the square roots of 5, I have a total of 3 square root 5. Yeah. Yeah. So like lots of different ways we can approach it. I'm treating this by saying that that square root of 5 is like a thing. Let's say it's a car. I've got 2 cars plus 1 car. I got 3 of those cars. I really wish the square root of 5 was a car. I would like, no, I don't want 3 cars. But I have 2 of this thing plus 1 more of this thing. So collectively, I have 3 of that thing. Now, what I think is really interesting is that all of our algebra books start off by doing this with numbers. But I actually find that most students feel more comfortable if I were to write this as 2 square roots of x plus another square root of x. Somehow it's easier to see that that's 3 square roots of x. But it behaves the same whether we're talking about numbers or letters. Let's get another example going. So if I had, how about trying to decide how messy to make this, but I'll do 15 square root of 15 over 2 times the square root. Five over 2. So my instructions are going to be the same. My instructions are to simplify. Now, simplify is really vague. Sorry. It's the instruction that we see most often. Really what that word simplify means is look for other algebraically equivalent ways to write this and see if there's any terms that we can reduce. There are different approaches for what to do here, but because I have multiplication and everything is square roots, one option I have is to put all of it under a single square root. And if I go with that option, then this would look like 15 times 5 over 2 times 2. Well, since we're talking about square roots, I'm looking for numbers that are perfect squares. Because I know that if I've got numbers that are perfect squares, those are things that will simplify. So I'm thinking about 1, well, 1's really not going to do much for me. 4, 9, 16, 25, 36, 49, right? I'm looking for those perfect square numbers. Well, on top, I do not want to multiply out 15 times 5. But what I can do is to think about the top and take that 15 and instead write that as 3 times 5 times 5 over 2 times 2. Like with many things in this class, if you don't need to write out these intermediate steps, I don't need to see them. If it helps you to write them out, cool. So I'm going to treat this as saying the square root of 3 times the square root of 25 divided by the square root of 4. And then 2 of those things I can simplify. The square root of 25 can become a 5. And the square root of 4 can become a 2. I'm going to make a quick, just be careful about your handwriting note. It's really easy if you're doing these things quickly to like maybe lose how far out your square root bar extends. So just be conscious of that and make sure that like mine didn't quite make it all the way past the 5. And it's possible that if I were looking at that on the next line, I might have thought that this 5 was already sort of outside of the square root somehow. Sometimes in the textbooks, they'll like give it a little tail to show, to kind of capture it all and make sure that you've got what you need under the square root. Just a few happy tricks. Question.
So let's say we
Mm-hmm.
would be
No, it's just to make sure that when you're looking at it, that you know what was inside of that square root and what wasn't. Yeah. More fun. So let me get another one going here. Again, our instructions are going to be to simplify. And I am looking at the square root of 80 minus square root of 32. Oh, good question. And just to quickly address in the previous problem, if this had worked out so that I had a square root of 3 on the top and a square root of 3 in the denominator, they definitely would cancel out. Yeah. Because they're the same number, right? I don't like to use cancel. I like to say square root of 3 divided by square root of 3 is 1. But let's take a look at this one, and then we can maybe do some more with division. So if my instructions are to simplify, the only thing I know how to do is to hope that somehow these can be rewritten with less stuff under the square root. Like I'm looking for those perfect squares inside. So this time I'm not going to go all the way to like straight up prime factorization, because really what I'm looking for in this context is factors that are perfect squares. So if I think about 80, for sure 80 is 4 times 20, and I'm going to take it because that 4 is a perfect square. But 20 I can break up even more, because 20 is 4 times 5, not 2. Yeah, cool. It's Monday. I'll blame it on Monday after the time change. Okay. So that'll work for me. So now I can think about that as saying the square root of 4 times the square root of 4 times the square root of 5. Or 2 times 2 times the square root of 5. Now I'm going to look at the 32 and look for something similar. And because I'm looking for perfect squares, I'm going to jump straight to that 32 being 16 times 2. I know it's a little weird that I'm writing these side by side. I apologize. It's just how it occurred to me in my head. It's kind of treating this as two separate things. So the square root of 16 is 4. So that's 4 square roots of 2. So if I like put that all together kind of on the same line, the first one, I've got 2 times 2. So I've got 4 square roots of 5 minus 4 square roots of 2. So the question in the chat is basically exactly what I wanted to get at, which is there really is nothing that I can do with this. That square root of 5 thing is saying that like I have 4 of these things and I've got 4 of this totally different thing that is the square root of 2. So if I try to subtract them, there's nothing I can do with that. I'm stuck. If you really wanted to, I guess you could factor a 4 out and write that as 4 times square root of 5 minus square root of 2. But I'm not sure it looks particularly simplified in that form, but you certainly could write it in that factored form. Question.
I
Oh,
will have the answer there, but it's kind of just like I'm looking at this and different places, trying to think of what would make sense.
yeah, so so from a very practical perspective, if you're working on homework, you can totally pull out a calculator, right? Like so one of the frustrations with algebra stuff is that there are like millions of correct ways that I could write this same thing. Really, at the heart of algebra, most of the time, we're just talking about different ways to write the same expression, which I know can feel really frustrating. Well, if you straight up have numbers, you could definitely put these into a calculator and subtract them and put this into a calculator and see that you get the same answer. And if you have X's in there, you might just have to play around with it to make it look like the thing that's in the back of the textbook. I don't have a fantastic solution for that. There are some online algebra tools that would allow you to put two equations in and ask if they are equivalent. And you'll either return a true or false. So Wolfram Alpha is one of those where you can put into equivalent statements or that you think are equivalent statements and ask if they're equivalent, and it'll either say true or false. But yeah, there aren't a ton of great tools. So some of this just does come down to playing with it until you've gotten into a place where it's matching the answer. So there's a question in the chat that I think is going back to like on this side, what I did versus on this side, what I did. And I don't know whether this is going to help. From looking at the original problem, and I know that because I have square roots, I'm trying to find numbers that are perfect squares. So I'm specifically looking for factors of 4, 9, 16, 25, 36, 49. I could keep going, but I'm not going to. I know that 32 is 2 times 16. I wasn't 100% sure that 80 was 5 times 16. But I was sure that I could write 80 as 4 times 20. So the reason that this side ended up being a 4 times 20, and then I broke it down more to be 4 times 5, is literally that I didn't remember that 80 was 5 times 16. If you remembered that 80 was 5 times 16, I would have jumped straight there. And that would have also worked. I don't know if that answered the question in the chat. Maybe it did. Okay.
So it kind of knows that is at least a perfect square, like maybe you can't figure out, like, oh, if two perfect squares with 80 or
Yeah.
would you still eventually get like the answer, or just like,
Yeah, you'll eventually get the correct answer if you just like peel off smaller numbers, right? So let's say that I had the square root of 135. I don't know what this is divisible by, except that I'm positive it's divisible by 5 because it ends in a 5 or a 0. So if I don't know what else to do, I can start with that prime factorization, right? I can start by figuring out that piece of it. This is 5 times something. And if I literally am like, yeah, 5 times something, what's the something? We can go old school and we can do long division. I can take that and divide it by 5. 5 times 2, I'd have a 10. I would subtract that. I'd end up with a 35. 5 times 7 is 35. So this is 5 times 27. And then I'd go, okay, well, neither of those are perfect squares. So I'm going to keep breaking it down more. 27 is 3 times 9. And now I finally have a perfect square. So I could treat that as the square root of 5 times the square root of 3 times the square root of 9. And that square root of 9 would give me a 3. By the way, if this were something in the back of the book, I am positive this would say 3 square root 15. Two things. Notation wise, if we have a number that sometimes the phrase that gets bounced around is like pulled out of the square root, meaning if we found a perfect square in there, notation wise, we tend to put that number at the front of the square root. And that's exactly for that reason of making sure that it's really clear that it's not inside of the square root. The other piece is whatever's left inside the square root, if you've already simplified all of the perfect squares, whatever's left in there, we tend to collect back together. So that's why we'd end up with writing this as 3 square root 15 in the back of the book. So yeah, if you don't see the perfect squares to begin with, you can just keep doing the factoring until you get somewhere. Since we're on the subject of answers matching the back of the book, I'm going to talk about something that I personally think we should call unsimplifying. There's a historical reason why we do this. We can talk about that. But let's say that we had some lovely fraction and we had simplified it down and we got this down to looking like 3 divided by the square root of 2. That is not what the answer in the back of the book will say. Historically, back before we had readily available cheap calculators, certainly before we all had a calculator we drug around with us everywhere, people used slide rules. If you've never seen a slide rule, it's okay. You could Google it. It's really not that interesting. I mean, it's fascinating historically and really was a tool that allowed civilization to do some pretty incredible things for years. It's just a tool, and that tool couldn't handle a square root being in the denominator. Literally, the reason that we rationalize denominators is because of the use of slide rules. I'm guessing no one in this room has used a slide rule before or ever plans to. So to me, this is a perfectly simplified answer. The answer in the back of the textbook is going to do this for no reason except history. The back of the book is going to say, we need to rationalize that denominator. Which means we're going to multiply by 1, and we're going to do it in such a way that the denominator will not have a square root anymore. So if I multiply the bottom and I have the square root of 2 times the square root of 2, if I were to recollect those together under the same square root, that would look like the square root of 4. And since the square root of 4 is 2, we have gotten rid of the square root in the denominator. Now, while I'm kind of joking, I mean, I'm not really joking. It literally is because of slide rules. When we do it with numbers, there are actually legitimate algebra reasons that we need to use this tool when it's not numbers and we have variables. So there are definitely going to be times in calculus where it is important that we have this as a tool. But there's really never a time that we need to do it with numbers. If you have the square root of a number in the denominator, I couldn't care less. You are welcome to leave it there. But you should also know that in order to check your answer in the back of the book, you're going to have to rationalize your denominator. And that's going to be true with any textbook. It's going to be true in a pre-calc textbook. It's going to be true in a calculus textbook. And that's really because of history. Yeah, I am right there with you. So someone has shared something in the chat and shared it anonymously. Maybe I didn't allow people to share publicly, but I will share it anonymously because yeah, I'm right there with you. Totally terrible to have to rationalize denominators in honors math and then follow this with proofs based off of old dead white men. Like, yeah, whatever. I'm with you on that. It does seem silly that we have kept this thing around when no one uses slide rules anymore. But just for practice, let's do some more. No, you know what we're gonna do? I'm going to throw some letters in the mix because that's really more how we're going to see all of this in calculus anyway. So same instructions, we're going to want to simplify. But this time what we're going to simplify is the square root of 9x to the 4th, y to the 6th. When we were doing this with numbers, the goal was to find a perfect square inside of the square root. And my goal is the same here, regardless of whether I've got numbers or letters. So I'm going to think about breaking this apart again as I've got multiplication. So I'm going to call that the square root of 9 times the square root of x to the 4th times the square root of y to the 6th. There are two ways to get through this. Embrace the fraction exponents or rewrite these things as perfect squares. I am going to go for rewrite as perfect squares first, and then I'll do it with fraction exponents, which is honestly how I think about it. I do it with fraction exponents. Square root of 9 is 3. And then this I'm going to rewrite as x squared squared. And then I'm going to rewrite that y to the 6th as y to the 3rd squared. So that I'm taking the square root of each of those. So I end up with 3 times x squared times y to the 3rd. I don't know why, but in my head, numbers belong inside of square roots, but letters belong with fraction exponents. And that's really, honestly, just how my brain thinks about this. So taking the square root of something is equivalent to raising it to the 1/2 power or to a 1/2 exponent. When we have an exponent raised to another exponent, that exponent rule says we're going to multiply. So this turns into 3 times x to the 4 times 1/2. And then I'm going to have y to the 6 times 1/2. 4 times 1/2 is 2, and 6 times 1/2 is 3. We're going to get to the same place either way. Just totally up to us. So one of the things just to be careful about is if the only thing we have going on inside of here is multiplication, we want to keep it so that the only thing going on in there is multiplication. If the only thing going on inside the square root is addition, then there's nothing we can do with the problem. The only thing that we're able to simplify when we've got square roots is if we have multiplication going on inside of the square root. Good times. We got like 4 minutes left. That is definitely enough time to do another fun one. I really hate simplify as an instruction. I don't know who made it up. I don't like it. Square root of 5x to the third y divided by the square root of 15x to the fifth y squared. So there are a couple questions in the chat that I want to address before I dive into this. And I'll just grab myself some space at the top of the page over here. But the square root of x squared, I know that earlier I said technically that's the absolute value of x. Let's not get that complicated right now. If we take the square root of x squared, that's just going to be x. If we need it to technically be the absolute value of x, the problem will state something. Our textbook is actually really good in this section. And anytime there are variables, it makes a statement that they're all positive. So we don't have to worry about the absolute value piece, but technically the square root of x squared would be the absolute value of x. And if x is positive, then we can just write the square root of x squared is equal to x. Yeah. So that's what's happening. That's where our square root and squared piece go away. And by the way, that's happening because if we think about this with our fraction exponents, if I have x squared to the 1/2, that's x to the 2 times 1/2, which is x to the first. So I happen to like fraction exponents. And we definitely want to be, okay, so now let's go back to this question that I wrote. There are lots of different ways that we can approach this. One option would be to put all of that under a single square root and simplify the fraction-y part first. Another would be to kind of mess with the top separately from messing with the bottom. But to address something in the chat specifically, one option on the top would be to take that x to the third. And I'm going to break this up into little pieces. So I've got square root of 5 times square root of x to the third times the square root of y. And one option we would have on something like that x to the third would be to write that as the square root of x squared times the square root of x. And as long as we're keeping that all as multiplication, we can definitely break that apart in pieces. So since I've got multiplication there, I can write that as the square root of 5. And then that square root of x squared part, that can become an x. And then I still have a square root of x and I still have a square root of y. This is not the only way to do it, but this is one option. And similarly on the bottom, we could break this apart into all of its little factors and say, okay, well, 15 is the square root of 5 times the square root of 3. And then that x to the 5th, we've got all kinds of choices of what to do with that. One option on that square root of x to the 5th, oh, hey, look, I've got a square root of 5 over a square root of 5. I could make that go away. This is what I get for doing the top and the bottom separately. Now I've got a lots of stuff to write and I'm out of time. So this could be the square root of 5 times the square root of 3, and that x to the 5th, I could treat that as x to the 4th times x. Square root of y squared, I'm just going to write as y. So I've got a square root of 5, a square root of 3, an x squared, a square root of x, and a y. These would cancel out and these would cancel out. And that probably still isn't the way that the answer in the back of the book would be written, because we'd have a square root of 3 on the bottom and need to rationalize the denominator. That was a lot. I am out of time.